Good morning. Today I am going to discuss about the properties of Fourier series. Around 5 properties I would be discussing today. So this is my 15th lecture in the series on signals and systems. In this lecture I am going to discuss about the 5 properties, that is linearity, time shifting, time reversal, time scaling, multiplication, means in time domain. Let us take the first property. Here I have two signals. One is x of t, whose Fourier coefficients, Fourier series coefficients are a case, where k equal to 0, DC component, then amplitude of first harmonic k equal to 1, k equal to 2, amplitude of second harmonic, etc. etc. I will go up to infinite. So a case means a0, a1, a2, a3, etc. up to infinite. Similarly, consider another signal, that is y of t, whose Fourier series coefficients are b case. Now what I will do, I will take a linear combination of these two signals, where a is a real constant and b is also another real constant. So now I have to prove that the Fourier series coefficients also add in the same proportion as they are added in the combination of the signals. Okay, so that is what we are going to prove now. Let us go to the proof now. In this, our assumption is the both x of t and y of t have the same period capital T. So as you know, the Fourier series representation is valid. It is applicable only for the periodic signal. So now what I have done, I have taken one periodic signal and I have taken another periodic signal y of t, both having the same period, that is capital T. Okay, so let us consider this linear combination ax plus by. Then substitute the Fourier series for these signals. So we will get two summation terms here, one for first signal, other one for second signal, because first signal is weighed by a, because a is a constant, so I can keep outside or I can keep inside also, it doesn't matter. Similarly, b is a constant, so I can push it into the summation. Now I have a common term here, e to the power of j k omega naught t, here e to the power of j k omega naught t, these two are common, so I will take the common term and combine these two, capital A small a k plus capital B small b k, and outside I will write the common term. So basically these are nothing but harmonically related basis functions. Basically these are the basis functions, and this is the amplitude of the basis function which you are adding in this summation. Okay, now I can say that this part, because this equation resembles the Fourier series equation again, whose coefficients are in this bracket term. That means this and the combination and this combination both form the Fourier transform type. So that is what exactly I have written it here. So we have proved the property now. Now let us move to the second property, that is time shifting. Consider a continuous time signal. CT means continuous time signal, which is shifted by t naught seconds. Then its Fourier series coefficients are shifted in phase by a term that is proportional to T naught and K omega naught. Okay, so this is what you have, and in this, so for a given T naught, if the T naught is fixed, that means only one shift if I consider, then the frequency here omega naught changes. So omega naught for a given fundamental frequency, I have k equal to 0 means 0, k equal to 1 means omega naught, k equal to 2 means 2 omega naught. Like that I have all the set of all harmonics here for a given T naught. So I have here the phase. What it means here is the phase is changing by this means for a given T naught, the phase is directly proportional to the harmonic number. That means it is proportional to omega naught and proportional to, it increases as the k number increases. It is linearly increasing with the frequency for a given T naught. So this is what we have to prove. So let us consider this signal. I have again the given signal x of t and its Fourier coefficients are AKs and the signal period is capital T, and when a time shift is applied to the periodic signal x of t, the period won't change. It is only the total shifting of the signal. There is no change in the period of the signal. So I can write here as y of t equal to x of t minus t naught. This is the equation which is, and I am calling this shifted signal as a new signal, that is y of t. Now consider the y and consider the Fourier series coefficients of y. Then the Fourier series coefficients of yt, let us assume that they are bk's. So y of t and bk's, they form the Fourier transform pair. And here given signal x of t and ak's form the Fourier series pair. Sorry, it is not Fourier transform. It is the Fourier series pair here. Here also it is Fourier series pair. Now, by definition of this, bk is given by 1 by t integration t. So this t at this position indicates that arbitrarily any period which is equal to the time period. It need not be aligned with first cycle, second cycle, third cycle, like that. Anywhere arbitrarily, I can take half cycle from the first cycle and half cycle from the second cycle. So that is the meaning of this one. So afterwards, what I am doing, this already we know this definition actually. So integration of the given signal means here delayed signal and the harmonically related frequencies. These two are multiplied and the multiplied signal is integrated. That means area under the curve and over a period of capital T. So because you are taking the total area, you want to find the average area that is divided by T is coming into picture here. Okay, so this is bk is nothing but the Fourier series coefficients of the new signal, that is shifted signal. Now I have written this here. I have as it is taken this expression from the previous slide. Now what I will do, I will substitute tau equal to t minus t naught. Now when I substitute t equal to t minus t naught, t becomes tau plus t naught. This is nothing but tau plus t naught. Okay, so now in place of t minus t naught, substitute tau here. Then in place of t here, you have to substitute tau minus t naught. This is what you have to substitute. Then here, if I take here d tau, if I differentiate this equation, d tau equal to dt, because t naught is constant. Okay, so this is what you have. So substitute dt with d tau. Okay, so now I have substituted everything here. Now I can separate this exponential term tau plus t naught is there. So tau term and t naught term I can separate. I can write it here like this, but e to the power of e to the power of minus j k omega naught t naught is constant. That's why it has come out, because with respect to tau, this is constant. So this term has come out of this integration. Now I have the remaining part like this, and x of tau e to the power of minus j k omega naught tau d tau. Tau is the variable of integration. Now after integrating, when I substitute here, after integration, what I will get here? I will get this ak only. This is what I will get here, because, so what is this here? This one. So this is nothing but Fourier series coefficient. This is the definition. This total thing. So from here to here, this is the definition of AK. So I have replaced that with AK here. So what is happening here? So in this, as I told you, this is what BKs are nothing but the Fourier series coefficients of the shifted signal y of t. Now, so this is BK. BK is nothing but this part. This is nothing but BK now. So that is what I am writing here. In place of BK, I am substituting this. In place of y of t, I am substituting here. So the Fourier series of the delayed signal is equal to the original Fourier series coefficients multiplied by e to the power of minus jk omega naught t naught, which is a phase shift term. This much is phase shifted. These AKs basically, these are the complex, AKs are complex coefficients. Okay, because you have e to the power of, in the definition I have e to the power of minus j omega naught t, correct? That's why either AKs or BKs, they are complex numbers. So by multiplying a complex number here with e to the power of j term, you are shifting the phase of this one basically. Okay, but if I take the amplitude, because the shift is there only in the phase, that means what is the phase for this complex number? Tan inverse real part divided by, tan inverse imaginary part divided by real part. Okay, so otherwise magnitude if I take, and the magnitudes of BK and magnitudes of AK both are same, because when the signal is shifted, the coefficients are shifted in phase but not their amplitudes. Okay, so that is what you have here. Then time reversal, third property is time reversal. As usual, I am assuming the signal x of t, whose Fourier series coefficients are AKs. Then if the signal is time reversed, if I take the image version, or if I take the lateral inverted signal, this is called lateral inversion in time. So if I take the lateral inverted signal, time reversed signal, so there are so many names for this. So the Fourier series coefficients, they also get flipped. That means, because I should not say flipped, yeah, they are flipped. So this is AK becomes A minus K. That means positive indices will become negative indices, negative indices become positive indices. So that is what is the property here. So now we have to prove this property. Basically, we have to prove this property. So take this proof, and here by time reversal, the time period is not going to change here. This is x of t, and x of minus t means substitute the t variable with minus t variable. So here there is a plus here, here it becomes minus because of minus t. Because of minus t, this becomes minus. Now this is what I have showing here, as it is I have taken from previous slide. Now I substitute k equal to minus m. So here minus m here. So this is minus m, and here this k also, it becomes minus m here. So minus m means here plus m becomes plus infinite here, plus infinite becomes minus infinite. So it doesn't matter order whether you are starting from plus infinite to minus infinite or minus infinite to plus infinite. So I kept here m equal to minus infinite to plus infinite. It doesn't matter here. Okay, it is only a sign reversal. Now I have a minus m, so minus mth coefficient of coefficient a, and here minus k, this minus k is becoming plus m here. Okay, so now what is this equation? Here I have a Fourier series equation again whose coefficients are a minus m. So that's why here, because minus m I used here, instead of that I can use k here, and here this becomes minus k, because it doesn't matter what index I am using, what index variable I am using, it doesn't matter. So I can say that from this equation I can say that these two form the Fourier series pair. So that is what I have written here. The property is proved. Now in this case x of t is arbitrary. If at all x of t is even, means it has even symmetry. Then what do you mean by even symmetry here? I have a signal like this. If something signal is like this, so the other part of the signal will look like this. Okay, and if the signal, let us say if the signal is like this, then like this. Okay, so both are, this is a signal, this is also the same signal, so that is called the even symmetric signal. So if x of t is even symmetric signal, what is happening here? So x of t equal to, this is x of t, this is x of minus t, left hand side. So right hand side equal to left hand side, that is what is written here. Okay, x of minus t equal to x of plus t. Then in that case what happens? A of minus k equal to a of k. Same thing, that means ak, the coefficients also are even symmetric. That means if I take a here, for example, let us take k equal to 0, k equal to 1 here, k equal to 2 here. Let us take a1 is this much, and this is the amplitude of a1. This is amplitude of a2. Now what happens here? I have even symmetry for this. So this is a minus 1 and this is a minus 2. So what it means? These are nothing but AKs. AK magnitude of AKs. Okay, so this is called even symmetry. That means if the signal is even symmetric, the Fourier series coefficients are also even symmetric. If the signal is odd, that means odd symmetry means here, for example, if I consider this signal, if I consider this, what is the odd symmetric part of this? It is time reversal and polarity reversal also. So this is the odd symmetric part. So that means this, let me change the ink. So this signal and this signal, polarity reversal signal, both are a part of the same signal. So then in that case, I call this as odd symmetric. So similarly, if that is the case, then what happens to these Fourier coefficients? So they also become odd symmetric. See here, a to the power of minus k equal to a to the power of minus ak here. That means polarity also has changed. This is what is the polarity change here because of this. Okay, so that is what I mean. These are the extensions of this particular cases of this property. Now, so let us discuss about the fourth property, that is time scaling. In this, if the continuous time signal is time scaled by a factor of alpha, then the Fourier series coefficients do not change. The Fourier series coefficients do not change, but Fourier series representation changes. So let us see the meaning of this one after proving the property. Let us consider the given signal x of t, whose Fourier series expansion is shown here, and let us scale the time signal by a real constant, positive constant alpha. In this case, let us say alpha equal to 2. Let us consider that alpha equal to 2. That means x of 2t we want to find. Then you have to substitute t equal to 2t. So that is alpha t. In this Fourier representation, you have to substitute t with alpha t. So what it means is, after substitution, you have to consider for a t variable, if I take the frequency variable is becoming alpha omega naught. So it means the fundamental frequency now it becomes alpha naught omega naught. Okay, alpha omega naught. Okay, this is the fundamental frequency. Now that means the original signal has a fundamental frequency of omega naught. Now the new fundamental frequency after scaling in time has become alpha omega naught. In this case, 2 omega naught. So what it means is the period proportionally it reduces because this is frequency has increased twice. The fundamental frequency has increased twice. So fundamental period will become half now because all t by 2 it becomes half. So let us see the consequences of this. Now for example, let us take uh, some signal. Let us take some original signal like this. 1 is not to the scale, -1 is the given signal. Then what are you doing? You are taking the alpha equal to 2. Alpha equal to 2 means its period becomes t by 2. So how I have to write it is basically when alpha is greater than 2, it is called compression. The signal becomes compressed to half because alpha equal to 2. So this is 1. So my signal becomes half of this. The width of the signal will become half of this. So this is 1 by 2. This is 1 by 2 because actual thing this 1 is transformed to half, -1 has become -half. So the signal is basically compressed. When the signal is compressed, the time period here it was t. Now the time period of this one has become t by 2. So why I am calling this as time period? Because this is a periodic signal, so it continues like this. And here if I consider this is again compressed, so it is like this. The signal becomes like this. Okay, so this is what you have. Now what happens to the Fourier series coefficients? So what is happening here to the Fourier series coefficients is, I am drawing this for the first signal x of t. I mean before time scaling, let us say the Fourier coefficients are like this. This is a1, this is a0. Let us say something like this. There is a dc term also here. A1 is this. Then let us say this is a2. This is a2. Okay, so this is a1, this is a2 at k equal to 2. This is a0. Similarly, I have a -1 this side and I have a -2 this side. Okay, let us consider this. Now after scaling, what happens is the fundamental frequency is becoming twice now. See here, fundamental frequency is becoming twice. So what will happen here? This a0 will remain same. I will draw with a different color. I will change to some other color. So this is A naught will remain as it is, and 2 omega naught. That means now A1 will occur here. This is A1 and A2 will occur somewhere here. Okay, so this is A2, this is A1. So frequency has increased. So they are basically going away compared to this, because it has come down, the time period has come down in time domain. The frequency has doubled now. So frequency has doubled means this is k equal to 0, this is k equal to 1. So the frequency spacing has changed, but actual A0 value, whatever A0 value previously, same A0 value here, but only spacing has changed. So similarly, that means the harmonics have widened up. The spacing between harmonics have widened up. So what it means is the representation has changed. That's why you have to call this as representation change, not the coefficient change. Okay, that's why we use the term representation change. So this is what I have given: original signal, time scale signal. If alpha equal to greater than 1, that means in our case 2 it is, so it is greater than 1 or anyway. So both the fundamental frequency and spacing between harmonics increases, correct? As I have shown in the previous figure, it increases. But if it is less than 1, the spacing will come down. That means in time, if it is less than 1, let us say 0.5, then in time what happens? So in time it will the time earlier, the time compression was there. When alpha equal to less than 1, what happens is it is dilation happens. That means time period increases. Because time period increases, the harmonics becomes closer. Just opposite happens here. Okay. So however, the FS coefficients, Fourier series coefficients, remain the same. Values will remain same. Only the spacing changes. So that's why the Fourier series representation has changed. You should say that the representation has changed because of the change in the fundamental frequency. Otherwise, the coefficients are same. So that is what is this property. Now, let us go to the next property, that is multiplication. So in this, we have x of t, one signal, y of t, another signal. Both are periodic with the same period t. That is what we are showing. We are taking like that. And if I take the product, it also has the same period. Okay. So then what happens to the Fourier series coefficients? So let us take here, I mean, it is a little bit involved one. You have to really put and substitute for equations, and you have to get it different kind of integrals, but in this case summation, because it is the discrete values. So here basically it is convolution. It is convolution. H of k, what it means is h of k is nothing but this operation. This operation. So what it means is A case and B case. AK and BK, they are complexly related in the form of convolution. So probably later you will study this convolution in more detail. And here probably this is the discrete, in fact you have to, let me change the color again. So in fact what you have to see is this is discrete convolution. Here whatever I have shown, in this place I will get integration basically. So convolution integral, in that case it is called. It is continuous convolution. So that is what in this case, because these are the continuous time signals, so this coefficients because A case and B case are discrete values, correct? So that's why here you will get discrete convolution. Otherwise, actual convolution means you have to go for integration. Okay, so I don't go details into this, but I will explain. This multiplication, I can call this as a modulation process, or I mean some kind of modulation process, you can say. And I will illustrate now what is convolution. I will consider the real numbers. Let us take a set of numbers x, real numbers 152, x equal to 152, x0 is 1, x1 is 5, x2 is 2. Similarly, we take another set of real values, that is y0 3, y1 4, y2 7. So I am taking two sets here. Now what I am doing, I am keeping the first vector or set of values as it is. Second set of values I am time reversing it. Time reversing means, see here, this is 152 as it is. Time reversal means this 3 becomes first one, 0th value, first value, and second value. So they are just reversed like this, time lateral inversion. So this is originally, this was y0, y1, y2, 3, 4, 7. Now it has become y2, y1, y0. So that is 743. 3, 4, 7 has become 743. Just for a change, I am using the variable y prime, y bar or y prime. This y prime of 0, y prime of 1, y prime of 2. So new y I am using after time reversal. Okay. So now if I want to shift this, let us say I want to shift this left by one position, then what will happen? What it means is index should be reduced by 1. That means 0 minus 1, it has become minus 1 here. 1 minus 1, 0. 2 minus 1, 1. So that means we have shifted this vector 743 towards the left. That is the meaning of this one. Now one more step, you shift to the left. Then what happens? Minus 1 minus 1 minus 2, 0 minus 1 minus 1, 1 minus 1 0. So after shifting further, I had 743. So you don't see this as a isolated numbers. Compare this with x and y prime. You have to compare these positions. Now see here, I have put it the same thing here directly after shifting two shifts. I kept like this. Now this is original sequence. This is the time reversal sequence shifted twice towards the left. Now what I will do, multiply these two. So there is 0 here, 0 into 7, 0 into 4, 1 into 3, 5 into 0, 2 into 0. So I have a summation here, 0 plus 1 into 3, this term, and here 0 and here 0. And then multiply and add all these products. Then I have 3 here. So this is, what is this position? This vector is at this position. So this is, I can take this as a k, for example, k equal to minus 2. So after multiplication, the output I am calling as another variable z. So z of minus 2 equal to 3 here. Okay. So same thing, you keep x as it is. Now shift this towards the right. That means k equal to minus 1. K equal to minus 1. So because you are shifting this side, so plus 1, you have to add plus 1 plus 1 plus 1. So it becomes, I mean, indices I am not changing here, I am just showing like this. But here the 743, it was here only 1 and 3 was overlap. Now after shifting to right, I have 1 4 here, I have 5 3 2 overlapping functions are there. Now when I take multiply and sum, 0 into 7 0, 1 plus 4 this term, sorry, 1 into 4 this term, 5 multiplied by 3 this term. So total 3 terms I have 1 0, then 4 plus 15 19, and if this goes here 2 into 0 again, this 0, so 19. So z of minus 1 equal to 19. Now take another shift. Now one more shift to the right, then it becomes, I am shifting like this, 7 4 3, they are aligned now. So this is the position k equal to 0. So we started with k equal to minus 2. Then we have shifted to right to get k equal to minus 1. Again I have shifted towards right to get k equal to 0. Now 1 into 7 plus 5 into 4 plus 2 into 3 all put together the summation equal to, the sum becomes 33. Now move further towards the right. So now what happens here? K equal to 1 now. The shift is plus 1 now. Now when you shift this 5 into multiplied by 7, 2 multiplied by 4, other things are zeros. So that's why I got 43. I got 43 here. Then after another shift towards right, I have only one overlap, that is 2 multiplied by 7, that is the term, and that is for k equal to 2. That means shift. Here I am using k for the shift purpose. So k equal to 14. So thus, if I start here, the starting z of minus 2, minus 1, 0, k equal to 1, k equal to 2. I mean shift basically. So I can say that this is shift equal to 0 here, shift equal to minus 1 here, shift equal to minus 2 here, and shift equal to plus 1, and for shift of 2 I got 40. So these are the indices of this convolution output. Okay, so that is how you will get the convolution. So it is a simple operation discrete wise, but a bit complicated if you want to explain if it is a continuous time signal. Okay, so let us you understand this. I think now it is very clear. So I have taken, if I take the product of two signals, their coefficients, Fourier series coefficients, they convolve with each other. That is the property of multiplication in case of Fourier series coefficients. So thank you.
Like, share and subscribe. Hit the bell icon for more updates.